Okay, this is Unit 6, Video 1, Polarity. So when we deal with polarity, we're dealing with a molecule that maybe doesn't have an even distribution of charge. So what it means is one molecule is more electronegative than the other. So remember, electronegativity means the ability of an atom to draw an electron or attract an electron in a bond. So when we have two things, one thing's bonded, it's more electronegative than the element it's bonded to, then it's going to pull the electrons towards the most electronegative element. So when we do that, we can classify molecules as being polar or being nonpolar. Okay, so when it's nonpolar, we've got an even distribution of charge, so they're going to cancel out, whereas with polar, they're not going to be even. We're going to have, in order to do polar versus nonpolar, we're going to have to draw the Lewis dot structure. So let's look at a few examples. If we were to do this right here, we're going to draw the Lewis dot structure for this. Okay, you would get this, and we know if we looked at this, this is a tetrahedral molecule. So we've got a very symmetrical molecule, but we don't have all the same atoms connected. So if we were to draw this to look to have its correct geometry, it would look like this. Okay, so what happens is the chlorine here is way more electronegative. We know hydrogens aren't very electronegative at all. They want to give up their electron. Carbon's going to be a little bit electronegative, but chlorine's highly electronegative. So what happens is we get a pull of the electrons, we get a dipole, where we're pulling the electrons towards the chlorine. So this creates a polar molecule. Okay, we don't have even distribution of charge because the chlorine's going to be slightly more negative because it's pulling the electrons closer to it than it is to the carbon. Now if we were to look at another molecule, maybe something such as carbon tetrachloride, we're going to get, I didn't draw my Lewis dots on that. Okay, if you look at this, these are going to have very similar shapes. They're both tetrahedral. So if we were to draw the molecular geometry for this, okay, we're going to get a tripod, which is the way with one sticking up on top is the way tetrahedral looks. But if you look at this, what happens is the pull here is even. Okay, chlorine wants the electrons, but they're going to cancel out because they're equal and opposite. So if they're equal and opposite in charge, they're all going to cancel out. What we're going to end up happening is we're not going to have a dipole occurring. So we would call this a nonpolar molecule because we have an even distribution of charge here. Now, some simple rules to kind of go over to figure out whether a molecule is going to be nonpolar or whether a molecule is going to be polar. So here, the central for nonpolar, there needs to be two categories that must be true. The first thing is your central atom must have no lone pairs. So as you see, you must draw the Lewis dot structure in order to determine polarity. Okay, if there is no lone pairs, next thing you need to check for is make sure that all the atoms connected to the central atom are the same. Okay, so if you look over here, back at carbon tetrachloride, okay, remember, when we're looking for lone pairs, we're looking for geometry, for polarity, we're going to look on the central atom. Okay, carbon has no lone pairs, and everything on the outside connecting to carbon is the same. So it's going to make this a nonpolar molecule. Okay, and then another just kind of general rule for nonpolar molecules is if you're going to have a hydrocarbon, they're always going to be nonpolar. Okay, so hydrocarbons are going to be something such as C3H8. Okay, hydrocarbons means it's a compound or a molecule only containing carbons and hydrogens. Okay, we get an even distribution of charge here. Okay, now if you look at polar, okay, polar is a little bit easier because if you don't have these two true for nonpolar, the only option is for it to be polar. So if there's lone pairs on your central atom, so if we were to look at something such as ammonia, if you were to draw the Lewis dot structure for ammonia, okay, you might say, oh, well, I have the same atoms connected, but we've got a lone pair on the central atom. This lone pair makes a dipole occur. So therefore, this is going to be a polar molecule. Okay, also, we have different atoms connected to the central atom. So if we look back at our first compound here, we don't have the same things connected to carbon. Okay, so therefore we don't have an even distribution of charge, so it's going to be a polar compound. Okay, and kind of a general rule of thumb, something that's going to have a high electronegative elements in the compound, it's going to tend to make the compound polar. So real quick, looking at kind of molecules that are going to be more highly electronegative. Okay, fluorine is the most electronegative element on periodic table. So we're going to kind of increase electronegativity as we go across the periodic table and up. So if you kind of can see in your compound that you have a highly electronegative element in there, more than likely it's going to be a polar compound.